Hello, this is Marilyn Rosales. Today, I'll be providing an overview of the Safety and Security Unit, also known as SSU for short, found on TI's F29 series of real-time MCUs. As a part of this video, I will cover an overview of the SSU key concepts, the different modes of operation, and the SSU tool. Now, you may be wondering, what is the SSU? Well, the SSU is a tightly coupled module that acts as a firewall between the C29 CPU and the rest of the device. It provides context-sensitive memory and peripheral access protection, runtime code isolation, multi-zone debug security, and handles secure firmware updates. With these features, the SSU enables users to achieve runtime safety and security protections in their application without sacrificing latency for real-time control. I'll explain more in subsequent slides how this is achieved. Firstly, let's talk about how the Safety and Security Unit works. So suppose you have a project. Within that project, you have a series of files, some header files and code files that contain the data and code for your project. For example, there is a C file that contains code that's responsible for executing your control loop code. You don't want other parts of your project to be able to alter or affect the execution of your control loop code. The execution of this code must be isolated from the rest of the content within your project and vice versa. This functionality of freedom from interference can be achieved with the SSU. Users can specify a region of code to only have access to certain regions of memory. These regions of memory are called access protection ranges, or APRs for short. A region can encompass flash memory, RAM, peripherals, and each APR has a start and an end address. You can specify whether you want these instructions for the defined subset of code to have write-only, read-only, or write and read access to the region of memory you have defined. Now, how exactly do these APRs get linked to a section of code or data? Well, this is done through the concept of links. Links are responsible for associating a context of code or data and linking that to one or more APRs. Up to 16 links can be defined within the SSU. An example of link usage would be having a link for your control code and another for, say, your ASIL-D level code. In this example, I have two separate files with different executions that I do not want interfering from one another. I can associate each respective file and its content, code, data, etc. with a link. APRs are then associated to that link. In this example, I have defined 3 APRs for link 3, which is associated to file 1. Thus, the instructions in file 1 will have access to APRs 1 through 3 because they belong to link 3, which has permissions to APRs 1 through 3. Similarly, file 2 will have access to the regions of memory covered by APRs 4 through 7 because I have associated those APRs with link 4 and file 2 is a part of link 4. Each time an instruction of code is called or an access to a variable or data occurs, the access protection logic in the SSU will cross-check the link that the instruction or data access belongs to and check its permissions. If that link has access to the region of memory where the code is being executed or where the data or variable is stored, then the SSU will allow execution. Otherwise, the SSU will prohibit access and generate a security violation error. In this way, context switching across links and APRs is automatically handled and does not require any user intervention to reconfigure permissions. In a system with a traditional MPU, workload can be implemented with either a task or an ISR. However, the MPU would need to reconfigure each time a task is switched by software through the task scheduler, that being some type of operating system or scheduler. This will add latency to the system because software needs to reconfigure the memory region protections, leading to extra software cycles. In traditional MPUs, ISRs run in a privileged mode, meaning they have full access to the memory and peripherals, no matter how the MPU is configured. This is potentially a security risk if it's not handled correctly. Unlike an MPU, SSU enforces access permissions in hardware based on the code that is being run. There is no runtime software reconfiguration overhead. For SSU, this switch of protections is happening in hardware, so there's no extra cycles or added latency that occurs. This is how the SSU is able to achieve runtime safety and security protections in an application without sacrificing the latency for real-time control. Now, with the SSU, there's also the concept of stacks. A stack isolates code execution contexts from one another, providing hardware safety and security isolation. You can have one or more links within a stack, but a link can only belong to one stack. As an example, I could have one stack that is associated with link 2, handling all OS related items, another stack that has link 3 and 4, which are all for my control loop code, and then lastly, another stack for my communications link. In this way, I can partition different groups of code execution and isolate them from one another so that they don't corrupt each other's stacks. All of this is being managed in hardware. At a device level, the SSU also has 4 zones. Zones are what govern debug access and firmware updates on the device. A user can set up a zone to only have certain access to specific stacks, links, and thus APRs. An example for a zone configuration could include one group at a company developing the OS and its related components. The stack, links, and APRs associated with this can be part of one zone. Anytime someone wants to access all of the software resources related to the OS, they would need a password associated with the zone in order to open up access. In a similar way, another group could be working on the control code, or a third party could be working on communication stacks and only want to access resources and software for their control application or communication stack. This can be isolated and done via zone and require a password for entry. So the SSU also has 3 modes of operation: SSU Mode 1, SSU Mode 2, and SSU Mode 3. By default, when devices ship from TI, the devices are in SSU Mode 1. In this mode, everything is open. There is no concept of APRs, links, stacks, or zones, meaning no safety or security is enforced by the SSU. This allows for code development with maximum debug capabilities. Once a user is ready to implement safety into their project, SSU Mode 2 can be utilized. In this mode, the SSU enforces APRs, links, and stacks. In the last SSU mode, Mode 3, enforces zones along with everything else from Mode 2. In SSU Mode 3, the device is at its most secured state. By default, debug access is closed, and in order to open up debug, a password needs to be scanned into the device for each of the different zones for which you want to debug access to. It's important to note that the SSU only governs the C29 system, and the hardware security module is independent. So as an overview of what we have covered today, there's a total of 64 APRs per CPU, and it's the APRs that define the memory ranges and associated read and write permissions. There are 16 links per CPU. Some of those links have special permissions, but it's these links that group executable code with memory range groups. There are 8 stacks per CPU, and stacks are responsible for isolating code execution contexts from one another, providing a separate stack pointer. And lastly, there are 4 zones that span the whole device, and zones are what govern device-level debug and firmware security updates. TI does have a free-of-charge SSU tool that is embedded within sysconfig, also known as the system configuration tool. Through this tool, zones, stacks, links, and APRs can be set up. It automatically generates the configuration for SecCFG and SSU based on the selections chosen in the GUI, leading to a seamless setup of the SSU. Now, in summary, the SSU enables users to achieve runtime safety and security protections in their application without sacrificing latency for real-time control. And this is due to the hardware protection scheme that the SSU offers and its closely coupled architecture with the C29 CPU. The SSU tool can also be leveraged to automatically generate a SecCFG based on the user's selection of SSU settings. Lastly, please refer to software examples in the F29 SDK for configuring the SSU and read the Implementing Runtime Safety and Security with the C29 Safety and Security Unit application note for details on configuring and using the SSU. Thank you so much for watching.